Welcome back to our system design series. In this episode, we are going to talk about one of the most fundamental building blocks of scalable systems, which is load balancers. By the end of this video, you will know exactly what a load balancer is, why it is essential for large scale applications, and how it ensures your systems stay available and reliable all the time. So let's imagine that you have an e-commerce system, or like an e-commerce store, and let's say that we have a lot of customers and clients. Okay, and these clients sends a request to our server, and let's say that your e-commerce is getting too popular and getting too successful, so you have even more clients that sending more requests to the server, and our server right now reaches its limits. So it's time to scale. So how we can scale? If we want to scale our server to be able to serve all the clients, we could do one of two things. We could add more resources. So basically, we can add more RAM, more CPU, etc. But there are some problem comes with that we have a physical limit. We cannot add RAM endlessly. There are a physical limit to which um the scaling will be and the adding of resources will be. And the other thing, this is quite expensive. And lastly, we have what we can call a single point of failure. So if we have only one server, so if this server went down, our application is lost. So the other solution is to add more machine. So instead of have one server that serve all the clients, we can have server 1, server 2, and server 3. Let's put all of them here. And let's call it server 2 and server 3. Okay. And right now the clients will send clients will try to send the request to each server, but how the clients can send the request to the server? We need something in between. We need something in between that will distribute all the incoming requests to the servers, so we make sure that each server get the same requests as the others. Also depends on its weight as well, and also we make sure that we lose no cache. And this is where sorry, go back. And this is where the load balancing come into place. LB, let's call it LB, and let's give it a different red color. And make this a red one. So again, imagine you are running an online store and suddenly there is a huge influx of users because of scale. You want to make sure that all these users can browse and buy without crashing your server, right? So this is where load balancers come in. Load balancer will distribute incoming requests across multiple servers, ensuring that no single server becomes overwhelmed. So what will happen is that the client will send a request. Okay, why is that big? Can I work with this? Why it's really big? I don't know. Let's work with that. So when client, it will distribute all the incoming requests to, let's make it different colors so it will be easier for you guys to see what's going on. And lastly, I guess I could make this one. Yeah, this will be better. And yeah, let's make this like greenish or something like that. Okay, so as we said before, a load balancer is a component that helps distribute traffic across multiple servers Think of it think of it like a traffic cop directing cars on a busy road to different lanes to prevent any one lane from getting too crowded. In system design, load balancers ensure that incoming requests, whether they are user clicks, API calls, or data processing tasks, are spread evenly across the servers handling those requests. So this is not only helps with balancing the load but also ensures reliability. If one server fails, the load balancer can reroute traffic to other healthy servers. So if server one just went down, the traffic will be rerouted of this client because this client is responsible to connect with this one. The traffic will be connected, for example, with server two, for instance. So this is how it's improved the availability, reliability, and performance of the system, and also overall the scalability. Um, Common examples of load balancers, including Nginx and Proxy, you can use like, and there is also cloud-based solution like AWS Elastic Load Balancer, which is ELB. And these tools help manage traffic effectively and efficiency, ensuring the availability and performance of your system. So let's try to answer another question, which will be when and why to use the load balancer. So when should we use a load balancer? The short answer, whenever your application grows beyond the capacity of a single server. As user demand increases, a single server might struggle to handle all incoming requests, causing slowdowns or even downtime. A load balancer helps you scale horizontally, meaning you can add more servers to share the load. And the other thing also, load balancers also vital for fault tolerance. If one server crashes, the load balancer will quickly divert traffic to other servers, ensuring minimal impact on the user experience. This redundancy makes your application more resilient to failures, improving overall uptime and reliability. There are multiple real-time examples like Netflix, where millions of people are streaming shows at the same time. Netflix uses load balancers to distribute traffic across their server clusters to make sure you get smooth, buffer-free viewing experience. Um, so, in system design, load balancers are often placed at front of the server clusters, acting as gatekeepers for all incoming requests. They help create scalable and fault tolerance architecture that can handle growth and unexpected traffic surges. So, understanding how to use load balancers is quite essential for designing systems that can grow while maintaining reliability. It's a key skill for developers aiming to build robust and scalable applications. So, to recap, load balancers are like traffic controllers for servers, helping distribute requests evenly to maintain performance and availability. We talked about the types of load balancers, when to use them, and how they play a critical role in in scaling and fault tolerance. We didn't talk about the algorithms that load balancer is using to handle the distribution of requests, but we will talk about that in a different series because I am thinking about creating a series only for load balancers to get in-depth overview of how they are working. So that's it for this video, and see you in the future. Welcome back. Welcome back to our system design series. In this episode, we are going to talk about reverse proxies, another crucial building block in creating scalable and secure systems. By the end of this video, you will understand what a reverse proxy is, how it works, and why it significantly improves the performance and security of your application. So, let's say that we have, let's make it bigger. We have a client that could be quite bigger, and the client want to send requests to the server. There are several issues right now. One of them is, or like the, I will say the main thing is the security concern, because we don't know if the client is an actual real client. Maybe it's just a robot, maybe it's just a hacker, maybe the client is sending a lot of wrong requests, maybe the client is overwhelming the server with too many requests. Let's say that we have multiple web servers. So we have more than one web more than one web server. So imagine that you're running a website with multiple backend servers that handle different tasks. You need a way to direct client requests securely and efficiently to the appropriate backend server. This is where the reverse proxy come into play. They act as an intermediate component or intermediate server between clients and your servers, managing traffic flow and providing an extra layer of security. So let's delete that. Let's see that we have multiple servers. Let's put it here. Let's say that this is server 1. Okay, let's make this quite bigger. And we have server 2 and we have server 3. And the proxy, it will act as an intermediate. Let me put the proxy here. No, this is too big. Okay, this is... Can I make this thicker? I guess there is a way. I don't know. So what will happen here? That the proxy will act as an intermediate component and server between the client and the web servers. It will redirect the request to the appropriate server, and also it will act as a security layer. It adds security to improve the security and the performance of the overall application. So a reverse proxy is a server that sits between the client devices and your backend servers. It receives requests from clients and forward them to the appropriate backend server, then sends the server's response back to the client. This helps manage incoming traffic, balance loads, and add also an extra layer of security by hiding the details of your backend infrastructure. So think of a reverse proxy like a receptionist's in a large office building. When visitors arrive, they don't directly enter the office area. Instead, the receptionist greets them, figures out what they need, and directs them to the correct office. Similarly, a reverse proxy routes requests to the right server, helping manage the load and security and securing the backend as well. So there are three main things we will get from using a proxy. The first thing we said multiple times is that improving the security of our web servers. We enhancing security because by sitting between clients and servers, a reverse proxy hides first of the IP address of your backend servers, making it harder for attackers to target them directly. It also helps filter out malicious traffic and acts as a shield against distributed denial of service attacks. The second thing, it's also do some sort of load balancing because reverse proxies often include load balancing functionality. They distribute incoming requests among uh, several back-end servers, ensuring that no single server is overwhelmed and thus improving the overall availability and reliability of your system. Lastly, we have caching. A reverse proxy also can also cache responses, reducing the need for repeated requests to backend servers. This helps decrease latency and speeds up the content delivery, especially for static resources like images and CSS files. And in real world example, one of the popular example of a reverse proxy is Cloudflare. Cloudflare acts as a reverse proxy for millions of websites, providing enhanced security and optimizing the performance of content delivery by caching content and its edge servers. Cloudflare reduces latency and blocks malicious traffic before it even reaches the backend servers. Also, there is Nginx. Another well-known example is Nginx, which can act both as a load balancer and reverse proxy. Many high-traffic websites use Nginx to distribute requests and add a layer of security between clients and backend servers. So, in system design, reverse proxies are typically placed between the client and the backend servers. They intercept all incoming requests and decide where to send them. This placement helps improve scalability, security, and performance. I would say that's it. So to recap, a reverse proxy is a server that acts as an intermediary between clients and backend servers. It helps enhance security, balance loads, and speed up content delivery. We also looked at some real-world examples like Cloudflare and Nginx, and discussed how reverse proxies fit in other systems. If you enjoyed this video, please make sure to thumbs up and subscribe and hit the notification bell so you never miss a video, and see you in the future. Welcome back to our system design series. In this episode, we are diving into the domain name system, DNS. Domain name system is a fundamental building block of the internet. By the end of this video, you will understand what DNS is, how it works, and why it's so important for connecting users to websites around the world. So let's start into it. First, let's say that we have a client here, and the client needs to send a request to a server. And the client has its own machine and the server has its own machine, and machines are connecting with each other using IP address. So if the client wanted to use the server, it has to have the IP address of the server. But when you go to the internet, you didn't type the IP address over Facebook servers to access Facebook. You do something different. You type just facebook.com. And this is what we call a domain name. And this is where a domain name system comes into play. So basically, instead of the client just send the IP address, which is not easy to be remembered, it differently. Let's just try to do it here. Okay. It will send the domain name to a domain name system, and the domain name system will send back the IP address that hold that domain name. IP. Oh, okay. Sometimes Miro does a lot of stupid stuff, to be honest. Yeah, exactly. IP address. So the domain name system will send back the IP address to the client, and once the IP address is obtained, the client will try to send the request to the server with its IP address. So think of the DNS as a phone book of the internet. When you type a website name like example.com or facebook.com or youtube.com into your browser, DNS is what helps translate that human readable name into an IP address that computer can understand. This process is essential because while we remember names, computers talk to each other using numbers. So let's try to answer the question. Okay, what is a DNS? The domain name system is a distributed database that translates domain names like google.com into IP addresses. Every device connected to the internet has a unique IP address, but remembering those addresses is not particular for humans, or basically DNS bridges that gap, making it possible for us to access websites without having to memorize long string of numbers. So an example for that, if you type, let's say, just let's put the text like that. If you type www.example.com, what will happen here in your browser? The DNS will resolve that into an IP address such as 192, let's say, dot 0, dot 2, dot 1, for example, like that. And your computer will use that IP address to connect to the correct server. Okay, so I guess we need right now to talk about how does it works. And it works in 5 steps. First, we have DNS query. And when you enter a domain name in your browser, a DNS query is sent out to find the corresponding IP address. The second thing will be the recursive resolver. Let me make this quite wider. The second thing would be the recursive resolver. This is a first stop for your DNS query. The recursive resolver acts as a middleman connecting other DNS servers on your behalf to find the IP address. And there is a root server. So the recursive resolver then contacts a root server, which directs the query to the correct top level domain server. For example, the .com server for .com domain, for example. And there is fourth TLD server. So the TLD server then points to the authoritative name server for the specific domain you're trying to reach. And lastly, we have the authoritative name server. The authoritative name server, finally, the authoritative name server provides the IP address for the domain, and recursive resolver sends it back to your browser, allowing it to connect to the correct server. So it might seem like a lot of steps, but this whole process happens in milliseconds, making the internet experience seamless for users. There are multiple types of record. There is EA record and 4A records for IP version 6. There are C name record, which is and there is also CNAME record, and there is MX record. But I guess this goes beyond our focus on the on this video, because we are just trying to understand what is a domain name system on high level, because this is in context of system design interview. You just need to understand how domain name system works on high level. So let's say that, so to summarize, DNS is like a phone book of the internet, translating domain names into IP addresses that computers can understand. It works through a series of hierarchical steps to resolve domain names, and it relies on various types of DNS records to perform its job effectively. Without DNS, the internet as we know it simply won't be accessible or reliable. So that's it for this video, and see you in the future. Hello and welcome back to another episode in our system design series. Today we are diving into a fundamental topic, which is database. We are going to know what is a database and why do we need it in system design. By the end of this video, you will have a clear understanding of what is a database are, why they are so essential, and how they fit in our bigger picture of understanding of our systems to build reliable and scalable systems. So first, let's try to know when we need the system design. Let's say that we have a client. Let's say clients, not one client. And these clients send requests to our web servers, or let's say to our server. Let's say that we have only one server. Let's try to make everything quite easy and simple. And let's assume that our website gets too popular. So we have more clients are sending requests to our server, and also they're storing their information and their data in our server. And right now, our server handles two things: it handles the traffic, it handles the data. But with time, we need to add another server. We need to add another server to handle only the data. This where we use database. So let's say DB to store, for example, let's say because we only have uh, clients that maybe only store the data to store users, for example. So if you think about this, a database is essentially an organized collection of data that can be easily accessed, managed, and updated. Think of it like a digital filing cabinet where information is stored in a way that makes it easy to retrieve when it needed. Databases are used to store anything from user profiles, transaction histories, protocol catalogs, to more complex relationships between different pieces of data. So if you have ever wondered why applications store and retrieve data from your social media post to your e-commerce orders, it's all thanks to databases. They are the core of almost every system we use today, making them an essential building block in system design. So, as we said, this is what is a database, and this is why we need them. We need to answer another question about the the types of database, because database can be relational and or non-relational depending on how data is structured and accessed. Basically, a relational database stores data in tables like spreadsheets with rows and columns, while non-relational database might use different structures such as document or key value stores, or maybe key value pairs, sorry, or graphs or documents, whatever it will be. So, and we will talk about that in a bit. I guess let's talk about next why we need databases, why it's so important. So imagine you have an e-commerce application that handles hundreds of thousands of users. Users need to browse the products, add them to their cart, and maybe place orders. All these informations, like product details, user profiles, order histories, needs to be stored somewhere, right? This what's make database an essential thing, because that's where database come in. Databases help to ensure that information or the information your application needs is always available, secure, and up to date, whether it's tracking inventory, managing customer details, or processing transactions. Databases provide a structured way to store and retrieve data efficiently and effectively. They help maintain consistency, reliability, and integrity, which are crucial in building robust systems. So next we need to talk about the two types of database. So we have mainly two types, a SQL database, and also we have no SQL database. The SQL database, these are relational databases, meaning data is stored in tables with defined relationships. They are ideal for applications that require structured data and complex queries such as financial systems or customer relationships management. We have next NoSQL. These are non-relational databases designed to store unstructured data and scale easily across multiple servers. They are perfect for applications like social media, where data is constantly changing and growing. So there's other important thing, when to choose what. So choosing the right type of database depending on your application needs, whether you need to the structured nature of your SQL for complex relationships, or the flexibility of NoSQL for rapidly changing data. So in system design, databases play central role. They are where all the critical information lives, where it's user data, product inventory, transaction history, or logs. Designing your system design architecture involves designing how data flows into or in and out of your databases, and how to handle scaling as user demand grows, and how to ensure availability even if parts of your infrastructure fails. And I would say, from my opinion, choosing the right type of database in your system design interview is the most important step, because if you missed that one, there's your interview is over. So let's talk about when to use SQL or NoSQL. I would say by default we choose SQL. This is by default, okay? We go all the time by SQL. They have been there for like over 40 years. They can manage a lot of things. So by default, we go with SQL. We go in NoSQL in some conditions. First, if we have a huge amount of data, if we have unstructured data, if we are not so sure about how our data will look like, if the needs of tables might not be present in our system. So these are the conditions that we need to understand and we need to put in our head in order to when to use SQL and NoSQL. So for instance, if you are designing a chat application, the messages between users need to store somewhere. The database ensures the messages are stored reliably, and you have a huge amount of messages, maybe billions of messaging daily. So because you have a huge volume in your data, NoSQL could be a great fit, because NoSQL, it's great in scaling horizontally. Let's say that we have a financial system that we need to make sure our transactions are going as best as possible. We need consistency. We need we need consistency. So I guess SQL databases will be a great fit for that. So to wrap up, databases are the backbone of almost every application. They store and manage and provide access to data, ensuring that systems can operate smoothly and efficiently and effectively. So in system design, understanding how to leverage databases effectively is a key to building a scalable and reliable system. So if you enjoyed this video, make sure to subscribe and hit the notification bell so you never miss a video, and see you guys in the future videos. Welcome back to our system design series. In today's episode, we are going to talk about blob stores or blob storage. They are a key component for managing unstructured, relatively big data in modern system. By the end of this video, you will understand what a blob storage is, why it is crucial for handling large amounts of media, and how it fits into system overall architecture. So let's say that we have our own system, we have the client, and this client is sending requests to like a web server. Let's say that we have a web server, and this web server will take the requests and perform some sort of read and write requests in that database. And let's say that our database storing information about the users, like email, passwords, stuff like that. Right now, our client or our user needs to update larger files like images, videos, and stuff like that. It is really tough and also expensive to store the files and this pretty big data into our database directly. So what we are going to use is to use a blob storage, and this blob storage, basically we store the image, and we will be able to store the link, like a URL link in the table of the database, to make sure that our system is as reliable and as scalable as possible. And this actually how it works in big systems. So we will use, let's say, no. What is this? Delete. Okay. We will use like a blob storage. And this blob storage will be able to store in it if any photos, any videos. So if you have ever uploaded a photo to a social media, or watched a video online, or even shared a document through a cloud services, you have interacted with a blob store. A blob store, or what is called a binary large object store, is used to store large files that don't fit well in traditional databases. Think images, videos, backups, and other types of unstructured data. A blob store is let's try to understand again what is a blob store exactly. A blob store is a type of data of data storage designed to manage large unstructured file. Unlike traditional database which stores data in structured formats like tables, a blob store is built to handle objects like photos, videos, audio files, and documents. The term blob stands for binary large object, and these stores are optimized for handling files that can be huge in size and do not follow a predefined structure. So right now, we need to understand something else. The prop storage are perfect for applications that need to deal with high volume of media files. For example, platforms like YouTube use blob storage to manage videos content, while Instagram uses it for storing millions of images to by uploading users daily. We might talk in the future how the blob storage works, because I guess we might have a system design video to design a blob storage. But for this series, I want to make everything as easy as possible and as short as possible as well. So maybe we talk about other things that why it's useful to use a blob storage in our system. And I will say the first thing, it will be the scalability. The blob stores are designed to handle massive volumes of data, making them an ideal choice for storing media that can grow quickly, such as user-generated content. Number two, cost efficiency. Storing large files in a blob store is often more cost-effective compared to traditional databases, as blob stores are optimized for cheaper storage of bulk data. And third is durability and availability. Blob storage offer high durability, ensuring that data is replicated across multiple locations to prevent loss. This means your files are safely stored even if there are hardware failures. Lastly, we have integration with CDNs. The blob stores are often integrated with CDNs to cache content and make it available to users faster to enhance the user experience or media heavy applications. So let's just to summarize everything. The blob storage are essential for managing large volumes of unstructured data like images, videos, and documents. They provide scalable, cost-effective storage solutions that are perfect for modern applications that deal with media-heavy content. By offloading these large files from your primary database, you ensure better performance and scalability, and also cost effectively. So we don't have to store everything in our database right now. So that's it for this video, and see you in the future. Welcome back to our system design series. In today's episode, we are going to explore distributed cache, a crucial tool for speeding up data retrieval and improving system performance. By the end of this video, you will know what distributed cache is, why it is so important for scaling system, and how it helps reduce the load on your system in your primary database. So first, what is a cache? A cache is in-memory storage that we used to store in it the frequently accessed data. It serves our data really fast, and it improve performance, and it reduce latency. So let's just take a quick example. Let's say that we have a client, and let's just create a small system, and this client sends requests to a server, like read and write request, and the server is sending the read and write request, like querying something, write something to the database. And let's say that our system is read heavy, so most of the requests or read requests to read posts, videos, and maybe whatever it will be. So in order to make sure that we're improving the latency, we will have like what we call cache. And the cache, it will be in-memory storage that we will store all the frequently accessed data. So if the client wanted to access, for example, a specific product, so the server first to go to the cache and see does the product is available in the cache. If the product is available in the cache, it will be served from the cache to the user directly, which improve the latency, which reduce the latency and improve performance, and also reduce the load on the database. By this one, we improved a lot our application, and our application is scalable and reliable. If the product is not in the cache, the server will try to get it from the database. Database will send it back. The cache will store it, and it will be sent to the client. For the cache will store it for future uses. So this is how cache works in high level. So think about the time you have interacted with a website that loads quickly. Big reason for that speed is often caching. A distributed cache takes caching to next level by distributing cached data across multiple nodes. This approach is key to keeping your systems both fast and reliable, especially when dealing with large numbers of users. So let's talk about what a distributed cache is doing. A distributed cache is a system that stores copies of frequently accessed data across multiple nodes, allowing for faster data retrieval and reducing the load on your primary database. Unlike traditional cache that sits on one single server, a distributed cache spreads data across a cluster of servers or nodes, making it highly available and scalable. The goal is to avoid repetitive queries to the database by keeping the most frequently accessed data close to where it's needed. For example, user session data, product catalogs, maybe some configuration settings are often cached to ensure they can be retrieved quickly without needing to hit the main database every time. So I would say distributed cache, you will use distributed cache like in every system design interview. I don't know if you know Memcache, which is really like Memcache and Redis. Resin is often the most popular distributed cache systems. I guess you will use it most of the times in your system design interview. It's really important to understand what is a distributed cache and how it works and actually how it works by, because in your system design interview you might be asked about how does this one work. So distributed caches uses techniques like sharding to split data across multiple nodes. This way no single server is responsible for the entire cache, which helps to maintain high availability and fault tolerance. If one node goes down, other nodes in the cluster can still serve the data, ensuring a smooth user experience. So let's try to understand some benefits of the cache. First is to improve performance by caching frequently accessed data. Distributed caches reduce the time it takes to retrieve information, leading to faster response times for users. Second, reduce database load. Offloading read-heavy requests to the cache means that your primary database can focus on more critical tasks like handling writes or complex queries. 3. Scalability. Distributed caches can scale horizontally, meaning you can add more nodes to handle increasing loads on your user base growth. 4. Fault tolerance. Since data is spread across multiple nodes, the cache can remain operational even if one or more nodes fail. So, to sum up, distributed caches are essential for speeding up data retrieval, reducing load on your primary database, and ensuring high availability and scalability. They help maintain a responsive user experience, especially in applications with high read demand and growing user bases. If you found this video helpful, please make sure to subscribe and hit the notification bell so you'll never miss a video, and see you in future videos. Welcome back to our system design series. In today's episode, we are diving into content delivery networks, CDNs. They are a powerful tool for speeding up content delivery to users around the world. By the end of this video, you will understand what is a CDN, how it works, and why it is so crucial for improving the performance and scalability of our web applications. And I would say it's a pretty important topic in your system design interview, so you should pay attention in this one. So, if you had ever streamed a video that will load a file or accessed a website that load instantly, there is a good chance a content delivery network was behind that experience. A CDN is designed to reduce latency and ensure that users can access content quickly, no matter where they are in the world. So let's assume that you are the client. Let's take an example. So let's say we have a client, and the client is requesting, like let's say a specific photo from the server. So the server will go to obtain this photo from a Blob Storage, for example. Okay. And when when the server once the Blob Storage is obtained, it will be sent back to the client. What the CDN will do is that the CDN will cache this image and will basically put it closer to a place which is closer to the client. So when the client try to see the exact same photo again, or any other clients trying to see the exact same photo again, and instead of going all of this process, which is quite long, that takes time as well, it will try to fetch it directly from the CDN, which improve the scalability, reliability, and user experience, and reduce the latency. So a content delivery network, or CDN, is a geographically distributed network of servers that work together to deliver web content like images, videos, and HTML pages more effectively and efficiently to users. And instead of fetching content from a single center server, a CDN will cache the content at multiple locations called edge servers that are closer to the end users. Okay, this is how it works basically. And by storing copies of the content on servers closer to users, CDNs help reduce the time it takes for data to travel between the user and the server, which is known as latency. This means faster loading time for websites, better streaming quality for videos, and an overall improved user experience. So let's understand how does the CDN actually work. So let's try to understand this again from scratch. Let's say that when a user makes a request, for example, by visiting a website, the request is routed to the nearest server edges in the CDN network. If the requested content is available on that server edge, it's delivered to the user immediately. This is called a cache hit. Okay, if the content is not available on the edge server, the request will be forwarded to the original server. Okay, this called a cache miss. Once the content is fetched from the original server, let's say from the Blob Storage, and it will be sent back to the user, and it will be sent to the client. Once the content is fetched the origin from the original server, it's also stored at edge server for future requests, reducing latency for subsequent users in that area. So overall, using a CDN in your system design comes with numerous benefits. The first thing, which will be reduced latency, because CDNs bring content closer to users by caching it at edge locations, which significantly reduce latency and speed up page load times. Number two, improved reliability. So with content distributed across multiple servers, CDNs can handle network congestion and traffic spikes more effectively, ensuring a consistent and reliable user experience. Number three, load balancing. So CDNs help balance the load on your servers by offloading requests to edge servers, reducing strain on your origin server and minimize the risk of downtime. And lastly, enhanced security. So many CDNs offer additional security features such as DDoS protection, which helps mitigate attacks by distributing the traffic across multiple edge servers. So a real world example of a CDN, which will be Cloudflare, is one of the most popular CDNs providers. Basically, it's offering both caching and security features. They also help delivery content for millions of websites, ensuring a quick access and protection against cyber attacks. There is also Akami, which is used by major streaming platforms to ensure smooth video playback for viewers worldwide. So CDN in the system design, CDNs are often used to deliver the static content such as images, CSS file, and JavaScript directly from the edge servers, while dynamic content is fetched from the origin server. This helps offload traffic from your servers and reduces latency for end users. So to summarize everything, a content delivery network or CDN are essentials for delivering content faster, reducing server load, and improving the reliability of your web application. They are a must-have for any system design that aims to provide users with fast, consistent experience, no matter where they are in the world. So if you found this video helpful, be sure to like it, subscribe, and hit the notification bell so you'll never miss a video and see you in the future. Welcome back to our system design art series. In these videos, we are going to explore late limiters, a crucial tool for protecting your system from overload, ensuring stability, and maintain a smooth user experience. By the end of this video, you will know what a rate limiter is, why it is important, and how to implement it in your system design interviews. Okay, so imagine you are running a website and suddenly there is a huge spike in traffic. Maybe it's because of promotion, or maybe it's due to like a distributed denial of service attack or DDoS attack. In either case, your servers are getting bombarded with requests, and if left unchecked, this could lead to system failure. This is where late limiters come in. They help control the number of requests coming into your system to keep things running smoothly. So let's take an example to understand how the rate limiter working. So we have a client, and this client is sending a request to the server directly. But might the server send too many requests to the server, and the server might not have the capacity to handle all of these requests, or might our client is not a regular client, it's just a like hacker or someone wants to put our server or our application in danger by sending too many requests. So we have to protect our server and our system from these attacks, or maybe also to make sure our users have a good and easy experience. Because let's say that if someone is sending too many requests, this will impact our system, also will impact our users experience as well. So what is happening here? So what will happen is that we have a rate limiter. So let's put the server here, and let's say that we have a rate limiter. And let's make the rate limiter quite big. So when the client is trying to send too many requests to our server, that the server cannot handle all of them, all the requests will go through the rate limiter first. If the rate limiter see like a pattern, or the rate limiter see the client has passed the requested, or like the legally authorized amount of requests per hour or per minute, let's say that the rate has a rule that each client should send 2 requests per minute, for example. So if our client sends 4 requests per minute, the rate limiter will reject the other 2 requests to make sure our system is secured and it's not overwhelmed with requests. So a rate limiter is a mechanism that controls the number of requests a client can make to a server over a specific period of time. By limiting the rate of incoming requests, you can ensure that your servers are not overwhelmed, and you can maintain consistent performance for all users. So rate limiters act as gatekeepers, preventing users from making too many requests too quickly. This is especially useful in public APIs, where allowing unlimited requests from a single user could consume excessive resources and negatively impact other users. So let's try. There is multiple ways of how actually the rate limiter working. There is like a token bucket, because in this algorithm, tokens are generated at fixed rate and stored in a bucket. When a user or when a request is made, it need a token to process it. If tokens are available, the request is allowed. If not, the request is blocked or delayed until tokens become available. There is a leaked bucket, and the leaked bucket algorithm controls the outflow of requests like water from a leak bucket, ensuring a consistent flow rate. Excess requests are either dropped or delayed until the bucket has capacity. There is um, a fixed window or sliding window. These algorithms count requests within a specific time window. The fixed window approach counts requests per defined period, like 100% per minute, whereas the sliding window provides a more flexible approach, tracking requests in overlapping time periods. And in the future, we will create a videos that talks about each of these algorithms in details, and we might code them in we might code them in the future. So these algorithms help you control the rate of the request, ensuring that your servers are not overwhelmed and can continue serving users reliably even under a high traffic conditions. So the benefits of using the rate limiting. First, preventing overload. Rate limiters help protect your systems from being overwhelmed by too many requests, which can lead to slow response times or even complete failure. Number two, ensure fair use. By limiting the number of requests a user or client can make, you can ensure fair resource usage and prevent a single user from consuming excessive resources and at the expense of others. Also, it has a DDoS protection. Rate limiters provide an initial layers of DDoS attacks mitigation by limiting the number of requests that can reach your servers, helping to protect against attacks aimed to overwhelming or overloading your infrastructure. And also, it also provide a cost control benefit, because rate limiting can also help control operational cost by reducing the load on your infrastructure, which is particularly important for applications that scale based on resources. Um, what is next? I guess we are done. To sum it up, rate limiters are essential for protecting your systems from being overloaded, ensuring fair usage of resources, and providing an extra layer of defense against DDoS attacks. Implementing rate limiting in your system design helps maintain stability and ensure a reliable user experience even during traffic spikes. So if you enjoyed this video, make sure to like it and subscribe more for more system design insights. In next video and next episode, we will explore distributing message queue. We might do that, or we might go into discover the microservices. I'm not so sure about it yet, but we will discover it later. So yeah, that's it for this video, and see you in the future. Welcome back to our system design series. In this episode, we are going to dive into distributed messaging queues, a powerful tool for decoupling services and enabling scalability in modern applications. By the end of this video, you will understand what distributed messaging queues are, why they are crucial for building scalable systems, and how they can help ensure reliability and flexibility in your application. So, imagine you are building a complex application where multiple services need to communicate with each other. For example, a payment service, an inventory service, and a notification service, for example. If these services talk directly to each other, it can create tightly coupled system that's hard to scale and maintain. This is where distributed message queues come in. They allow you to decouple services, making your architecture more resilient and scalable. So let's take an example to look at how to look on how distributed messages looking are. So we will have like a service, let's call it a producer. producer, and let's call it producer 1. Let's say that we have multiple producers. Okay, and they will send requests through message queue. Let's change the okay, let's make it like that. And if I made it, I guess, and let's make all the color for it red. So they will send the request through the message queue, and we have consumers. Let's copy this one, and let's say that we have a consumer. And this consumer will pull these messages from the message queue. So by this, we enabled asynchronous communication. Let's make a different color. Let's add another one here. And last one. Okay. And let's say that we have consumer 1, consumer 2, and consumer 3. So a distributed message queue, as you can see, allows for asynchronous communication between different parts of the system by sending messages between producers and consumers. They help decouple services, ensuring that even if the consumer is unavailable, the producer can continue sending the messages. Okay, so if we're trying to understand this one, like imagine you're building a complex application where we're like where we have multiple services are communicating with each other. So the order service, maybe notification service, and multiple services. And instead of them connecting with each other directly, this will be quite tough. We enable asynchronous communication with message queue. So the service could send a message to the message queue, and the other services could pull this message from the message queue. So this decouples the services from each other, which means that they can operate independently. If one service is down or slow, the rest of the system can continue functioning at the messages as the messages are held in the queue until the recipient service is ready to process them. So we can, I guess, by far right now, I guess we know what is a message queue. A message queue or a distributed message queue is a system that allows different components of an application to communicate by sending messages through a centralized queue. And instead of having services directly communicate with each other, they send the messages to the message queue, which then routes those messages to the appropriate recipient. Okay. We might ask ourselves another question, like how does message queues actually work? So we have services that are producers, which are produce the message. We call them producers because they produce the message. Called producers send the messages to the queue. Okay, let's send the messages to the queue. Other services, which called the consumers, then read those messages from that queue and process them. The queue acts as a buffer to ensuring that messages are delivered even if the consumer is temporarily unavailable. So this mechanism allows for asynchronous communication between services, which is especially useful when processing tasks that take long time, such as generating reports or sending bulk notifications. With a distributed queue, producers can continue sending messages without having to wait for consumers to process them, which improves the efficiency and responsiveness of the entire system. So if we right now we know what is the message queue and also we know how it works, we need to know what is the benefits from using a message queue. The first thing is decoupling services. By using message queue, you can decouple different parts of your system, making each component more independent and easier to maintain or replace. The second thing is scalability, because distributed message queues help scale systems by allowing multiple consumers to process messages concurrently. You can easily add more consumers to handle increased load. Lastly, fault tolerance. Message queues are stored in the queue until they are successfully processed by consumer, providing fault tolerance. If a consumer fails, the message remains in the queue, ensuring that no data is lost. And lastly, load balancing. Multiple consumers can process messages from the queue effectively balancing the load across different services and ensure that no single service become a bottleneck. A real world example of a message queue is Apache Kafka, is a popular distributed message system used by companies like Uber to handle millions of rides events in real time. And Kafka's, I guess it's the most famous one. The most there is a RabbitMQ as well, but I guess Kafka is the most important one and the most used one in my opinion. So, to summarize everything, a distributed message queue are a powerful tool for decoupling services, improving scalability, and ensuring fault tolerance in your system design. They enable asynchronous communication, which helps build resilient and scalable systems, especially in complex architecture with multiple interacting services. If you enjoyed this video, don't forget to like it, subscribe, and hit the notification bell so you'll never miss any video, and see you in future videos. Welcome back to our system design series. In today's episode, we are going to discuss microservices, a popular architecture style that helps build scalable, flexible, and resilient systems. By the end of this video, you will understand that microservices are what microservices are, their advantages, and how they fit into modern system design. And it will be pretty important aspect of your system design interviews. I guess you will use microservice a lot. So let's say that imagine you are building a complex application like an e-commerce platform. It has multiple functionalities: user registration, product catalog, order processing, payment handling, and more. If all of these functionalities are built together as a single application, any change or failure in one component can impact the entire system. This where microservices come into play. So let's go down here and say, instead of having like one big server or one big system that handles everything for us, we will break this system into smaller, more manageable pieces. So if we have a e-commerce platform, we'll have a user service. Okay, user service. We will have as well, like let's say that a product service, and we have like a product service. We could have like let's say that maybe on another one, which is, for example, an order service. Of course, in a real world e-commerce, we might have more services than that, but let's assume that we only have 3 services. So instead of having one big server that handles everything, we will have multiple services that handles each that handles one functionality or one aspect. So micro, like as you can think about it, if all these functionalities, for example, build together in one server or one single server, any change or failure in one component can impact the entire system. And if we're using a microservices, as you can see on the right side here, microservices basically are an architectural style where an application is broken down into smaller, independently deployable services. Each microservice is responsible for specific business capability, such as user management, product service. Maybe we can add handle payment, order processing, and these services communicate with each other, often through APIs, maybe a message queue, like we use a message queue so they can communicate with each other with in the producer consumer style. And by breaking down application into smaller services, microservices enable independent development and deployment. This means that teams can work on different parts of the application simultaneously using the technologies that best fit for their needs without being tied to that tech stack. So in a microservice architecture, each service runs independently and can be deployed, update, or scaled without affecting the other services. Communication between microservices or happen through like a REST APIs or maybe like a gRPC or message queue like Apache Kafka. This approach makes the system more modular and easier to manage. So this is an example of how it works. So if we have a problem in the user service, the only user service will be affected and the other services will continue to operate as expected. So by this one, by using microservices, right, first it's easier to scale. It's our system right now. It's more resilient. Our system right now, if it can provide better availability instead of having one server when it has a problem, everything will be lost. So we don't have any single point of failure, as you can see. So for example, when a user places an order in an e-commerce website, the order service communicate with the inventory service, for example, to check the availability, and the payment service is here to process the payment, and the notification service to send confirmation email. Each of these services operates independently but works together to fulfill user requests. So let's understand what is the benefits from microservices. And I would say the first thing will be the scalability. Scalability. Microservices can scale independently based on demand. For instance, if the product catalog service or if the product service, for example, this one, um, getting a lot of traffic, you can scale it separately without affecting the other services. Also, the second benefit that we get from microservices will be the flexibility in technology. Different microservices can be built using different technologies that best suit their needs. You can have one service written in Java and another one in Python, allowing teams to choose the best tools for the job. And three, we have resilience. Like, since each service runs independently, the failure of one service doesn't bring down the entire application. For example, if the payment service goes down, users can still browse products and add them to their cart. And number four, I didn't put this on. And number four, it will be the faster development and deployment as well. The faster development and deployment. Teams can develop, test, and deploy individual services without waiting for changes into the entire application, leading to faster release cycle and more agile development. Basically, if we want to take an example for that, I guess Amazon is a great example of microservices architecture. Amazon is a great example of a company that successfully transitioned from a monolith architecture to a microservice architecture. Like, each part of Amazon platforms, like the product search, payments, and recommendations, is managed by a separate microservices, allowing for better scalability and resilience. Another great example, I guess, it will be Netflix. So I guess which adopt microservices to handle the massive scale of streaming content to millions of users worldwide. By using microservices, Netflix can independently scale and update its services, ensuring a seamless viewing experience even under high load. So, in your system design interview, I guess microservices are often used to build complex distributed systems where different services can evolve independently. For instance, in a ride sharing application, if you will design something like Uber, you can have a separate microservices for driver management, ride matching, payments, and notification. This modular approach make it easier to a new feature or modify existing ones without disturbing the entire system. um, Okay, so we might see some challenges in the microservices. It's important to talk about that as well. The first one, it will be the increase in the complexity, because the increase in the complexity, it's a big one here, because managing many independent services can be quite complex. Each service needs its own deployment, monitoring, and scaling strategy. The second thing, it will be the communication overhead. Since microservices communicate over a network, there is added latency and potentially points of failure compared to process communication in a monolithic system architecture. And lastly, which is the data management. Ensuring data consistency across multiple microservices can be quite challenging, especially when each service has its own database. We will talk about that in the future, on about how to microservice in details, and what are all the challenges and how to solve them in details. But for now, we're only talking about microservices on uh, on high level. So to summarize everything, microservices are architectural style that helps break down complex application into smaller independent services that can be developed, deployed, and scaled independently. They offer great benefits in terms of scalability, resilience, and faster development cycles. But they also come with challenges like increased complexity and communication overhead. So if you found this video helpful, make sure to subscribe and hit the notification bell so you never miss a video, and see you in the future. Welcome back to our system design series. In today's episode, we are diving into distributed unique ID generators, a critical component for generating a unique identifiers across distributed systems. By the end of this video, you will understand what distributed unique ID generators are, why they are needed, and how they help ensure consistency and reliability in large-scale systems. So, imagine you are running a large distributed application, like a global e-commerce platform. You need to generate unique identifiers for orders, users, products, and transactions across multiple servers. But each of these servers needs to generate IDs without any conflicts, basically. This when a distributed unique ID generators come into play. They ensure that each entity in your system gets a unique identifier. So no matter where and what and when it's generated. So let's take a quick example. Let's say that we have multiple servers. We have a user service, user services, and we have again also order services, that it's distributed across different services, different servers, and we have product. And for each service has its own database, and we need to create and generate IDs, so no user have the same ID in other database, because we have a distributed systems. So we will connect with like ID generator. S- let's see, let's give it a name, a unique ID generator. Okay, so they will connect with the unique ID generator, and they will obtain their IDs from it. So a distributed unique ID generator is a system that generates unique identifiers across distributed environments. The challenge is in a distributed system is that multiple servers may need to generate IDs simultaneously, and it's crucial to avoid collisions, or like meaning no two entities should end up with the same identifier. So let's just try to think why this is needed. So if you think about it, these IDs are used to identify records to like user accounts, orders, transactions, products, and more. The main goal is to generate a unique ID, a unique, consistent, and fast, even if the application is operating across different data centers or regions. And if you try to think about it, let's try to get an example. If in a traditional system, generating a unique ID has been often handled by that centralized database. So let's say that we have our own DB and we add records to this one, to this DB, and basically we will generate the IDs. It's a pretty obvious. It will be generated by increment. So we have one, two, three, four, etc. However, in distributed environment, relying on a single point to generate ideas can be quite a bottleneck and a single point of failure. So, because of that, we use a unique ID generator, and a distributed unique ID generator helps solve this problem by allowing multiple servers to independently generate IDs without the need for centralized source. This ensures that your system can scale horizontally and remain resilient even if individual servers experience an issue. So there are multiple ways and multiple there are common like several common approaches to generate distributed unique IDs. There is the first one, which will be the UUID. UUID. UUID is a universal unique identifier. UUID are about, I guess, 128 byte. The UID one is 128 byte. It's identifiers that are designed to be unique across space and time. They are often used when you need a high level of uniqueness without coordination. However, they can be quite large, which might be inefficient in terms of storage. The second thing will be the Twitter snowflake. Um, the Twitter Snowflake is an ID generation system developed by Twitter. It generates, I guess, the ID is about like 64 bits, so it's a pretty smaller than the other one. The 60 it generates the 64 bits IDs that are timed, ordered, and unique. Each ID is composed on a timestamp, data center ID, worker ID, and a sequence number, which makes it easy to generate IDs that are unique and can be stored like I, chro- chronologically. The next thing is to talk about is the database sequence sharding. This one, I guess, is not that famous in my opinion. Most of your in system design interview, I guess, you will be asked about the Twitter Snowflake, but let's talk about the database sequence sharding. In this approach, each server or node is assigned on a range of numbers it can use for generating IDs. This is a really important aspect, but I guess in your system design interview, you will not be asked about database sequence sharding, or from my experience, at least I wasn't asked about database sequence sharding when it comes to talking about distributed ID generation. So in the system sharding, in this approach, each server or node is assigned on a range of numbers it can use for generating IDs. This allows multiple servers to generate unique IDs independently by ensuring each one works within assigned range. So one shard has ID from like 1 to 10 to 100, for example, and the other have like from 100 to 200 and etc. This is how it works basically. Um, so these methods allow distributed systems to generate unique identifiers in a way that is scalable, efficient, and collision free. Each method has its own trade-offs in terms of complexity, storage, and ease of use, and depending on the specific use cases. So let's talk about why the key benefits of using a distributed ID generators. So it comes, I guess, in my opinion, for four things. The first one is scalability. Let's try to scalability. I want to see if I can still write. But I guess my writing skill is quite it's improving in on Miro. So the first thing is scalability. Distributed unique ID generators allow your system to scale horizontally with multiple servers independently generating IDs, avoiding bottlenecks. And the second thing also it will be fault tolerance tolerance tolerance. Okay. So since IDs are can be generated without relying on a centralized or central server, the system remains operational even if one or more servers goes down. The third one will be uh, the order perseveration. Like some ID generation methods like Twitter's Snowflake generate IDs that are time ordered, which can be quite useful for maintaining the behavior and the look and the information of the order and the order of the events. The last thing will be global uniqueness. Distributed unique ID generators ensure that each entity in your system has a globally unique identifier, which is crucial for data consistency and avoiding conflicts. So I would say that to sum it up, a distributed unique ID generators are essential for creating a globally unique identifiers in distributed systems. They help ensure that your system is scalable, fault tolerant, and capable of maintaining data consistency, whether you use UUID or Twitter Snowflake or database sharding. These tools are crucial for managing unique entities in large scale applications. If you found this video helpful, don't forget to like it, subscribe, and hit the notification bell so you'll never miss a video, and see you in the future. Welcome back to our system design series. In today's episode, we are going to explore the publish and subscribe systems or pub subsystems, a powerful architecture pattern used to enable real-time communication between different components of a distributed system. By the end of this video, you will understand what a PubSub is, um, why why it's important, and how it helps decouple producers and consumers in modern applications. So, imagine you are building a social media application platform where users need to get real time notifications about new posts, likes, or comments. If every user action has to be communicated directly to every other relevant user, your system could quickly become overwhelmed and difficult to scale. This is where a pub subsystems comes in. It enables efficient and scalable real-time communication between producers and consumers. So let's take an example of a pub subsystem. So first we will have a producer or publisher. Let's call it publisher. And I guess I put the I guess I don't know. No, this is the B for book. And they will send the publishers will send all the new the like notifications, events, and stuff to the topic, and the topics will send consumers. Let's consumer one. We have consumer two. And we have consumer 3 as well. 2 and 3 and yeah. So let's put this one here. And let's put this one here. And yeah, make it like that. Okay, it looks good. So a publish subscribe system or pub subsystem is an architectural pattern that allows one-to-many communication between different parts of the system. In this pattern, producers or publishers sends messages to a central topic or channel, while consumers called subscribers receive those messages by subscribing to a specific topics. The main advantage of the pop-up system is decoupling. Publishers don't need to know who those subscribers are, and subscribers don't need to know where the messages are coming from. This allows for more flexibility, scalability, and easier to maintenance. So in pop-up system, publisher sends the messages. As you can see, the publisher will send the messages to the topic, and or the channel, which acts like a mailbox, and the subscribers can choose to receive the message from the topic they are interested in. When a new message is published, it's immediately distributed to all subscribers of that topic. So by then we can send all notifications, posts, likes, comments to all the users and the consumer that are interested in this specific topic without overwhelming our systems with too many requests. So this kind of asynchronous communication is ideal for real-time systems where you need to broadcast information to multiple services or users, such as in notification systems or event-driven applications and streaming data pipelines. So first, let's talk about some key benefits from using this. The first thing, as we said before, is decoupling. Decoupling. So pop-up systems decouple producers from consumers, which makes the system more modular and easier to scale. Publishers simply send messages to topic or to specific topics without worrying about the subscribers. The second thing will be scalability. So pop-up systems handle large volumes of messages efficiently and effectively, allowing multiple services to process the same event without creating direct dependencies. And lastly, we have real-time communication. Communication. And yeah, let's I will not write it all, so I will not make the video quite long for no reason. So pop-up systems are designed for real-time communication or real-time data distribution, making them ideal for applications like chat systems, live notifications, and IoT. And lastly, it's important also for fault tolerance. Fault tolerance. What's this? Scalability for tolerance. I don't know why I did write this, but let's continue with this. It's important for fault tolerance because pop-up systems often use message brokers that can persist messages, ensuring that subscribers receive the messages even if they were temporarily unavailable. For example, and we might talk about some real-world example, like a well-known example of pop-up system is Amazon SNS or Amazon Simple Notification Service, which is used to send notifications from publisher to multiple subscribers, such as mobile devices or email addresses or other users or user services. And another example, I guess, is Google Cloud Pops Up, which is used by companies to build event-driven system and process streaming data, and it helps basically applications respond in real time to new events such as logging, monitoring, and analytics, and yeah. So yeah, what next thing that I should talk about? Yeah, there is something important that while pop-up systems are incredibly powerful, they come with some challenging. First is the message ordering, because maintaining the correct order of messages can be quite challenging. The second thing is the message delivery guarantees, like depending on implementation, a message can be delivered at least once, or exactly once, each of which has its own trade-offs. And three, complexity is in decoupling, because decoupled nature of PubSub can make it harder to trace the flow of messages, making decoupling more complex. So to summarize, pub subsystems are powerful architectural patterns that enable one-to-many communication between different components in a distributed system. They help decouple producers from consumers, support real-time data distribution, and make it easier to scale and maintain complex applications. However, they do come with challenges like managing message order, and ensuring reliable delivery. If you found this video helpful, don't forget to like and subscribe and hit the notification bell, and see you in future videos. Welcome back to our system design series. In today's episode, we are going to discuss distributed logging systems, a crucial tool for monitoring and troubleshooting complex distributed applications. By the end of this video, you will understand what distributed logging systems are, why they are essential for maintaining system health, and how they help identify and resolve issues in distributed environments. So, imagine you are running a large-scale distributed application composed of dozens of microservices. So let's create that. We have a lot of microservices. We have a user service. Let's make this quite wide. And we have a profile service. We have, like, let's say that a product service. Let's say we are running a e-commerce platform, and we have maybe an order service. Maybe we have like an invoice service. Invoice service. We might have another one which is like inventory service, inventory, that tracks the inventory of the products. So we have all of that services. So each microservice generates like logs that contains important information about its health, error, and event. Okay, so without a distributed logging system, it would be incredibly challenging to gather, search, and make sense of these logs, especially when debugging issues that span multiple services. So this is where a microservice logging system comes into play. So let's just put all of this services first in one big container. And distributed, okay. And let's put it like that. So by this is how it will look like in your system design interview, or I guess it will not look exactly like that, but it's close to that. So a distributed logging system is a centralized solution that collects and aggregates logs from multiple services or nodes in a distributed application. And instead of each service manage its own logs independently, a distributed logging system brings all logs together, making it easier to search, analyze, and correlate events across different services. This approach is particularly useful in microservice architecture, where you might have many independent services generating logs. By centralizing these logs, distributed logging system provides a unified view of the entire application, making it easier to monitor, troubleshoot, or analyze performance issues. Okay, so let's try to understand how does it work. Okay, we know what is a distributed system. We know how it will look like in a system, but let's try to understand how does this one work. So in a distributed logging system, each service or node generates logs. Okay, so for example, let's say the user service, it will generate, oh no, it will generate its own logs. Okay, and which are then sent to a log aggregator. The log aggregator collects these logs and send them to a centralized storage where they can be indexed and analyzed. Like tools like Logdash are often used to collect and transform logs, while Elasticsearch is used to store and index them for easy searching. So it will create logs. It will be collected by a log aggregator, and then it will be stored in a centralized storage, and we can use an Elasticsearch to store and index these logs. So it's a pretty easy process, and you will find that each service can create its own logs, and it will end up being stored in in one centralized store to make it easy for us to like index them, search them, analyze them, etc. So users can then interact with logs through a dashboard or visualize tools like Kibana or Grafana. This allows developers and operations teams to keep quickly search for specific log entries, create visualization, and set up alerts for user behavior. So let's talk about the key benefits of using distributed logging systems in our systems. The first thing, I guess, it will be the centralized visibility. With all logs collected in one place, you get a complete view of your distributed systems, making it easier to spot issues that span multiple services. The second thing will be the improved troubleshooting. Distributed logging systems help you trace requests as they move through different services. This is crucial for identifying the root cause of issues, especially in complex systems. The third thing, it will be, oh no, the third thing will be a real-time monitoring. So logs can be monitored in real time, allowing you to detect problems and respond quickly before they impact users. Historically, and lastly, we have historic analysis. Historic analysis. Logs can be retained for long periods, enabling historic analysis to identify patterns, trends, and recurring issues. One popular example of a distributed logging system is the ELK stack, which stands for Elasticsearch, Log Stash, and Kibana. The ELK stack is used by companies like Uber to collect, store, and analyze logs from their vast network of services, making it easier to troubleshoot and optimize performance. Another example is Splunk, which provides an enterprise-grade solution for distributed logging and monitoring. Splunk is often used by companies to gain insights into the health and performance of their application, as well as a security monitoring. Um, I would say, and lastly, in distributed systems, in system design, distributed logging systems are essential for maintaining visibility across multiple services. For example, in a microservices-based e-commerce platform, a distributed logging system can help track users' requests from the time they click checkout to when the order is processed by the payment service, inventory service, and fulfillment service. So it's a pretty important way to understand what's going on in your system. So to sum it up, distributed logging systems are essential for monitoring, troubleshooting, and maintaining visibility in complex distributed systems. They provide centralized visibility, real-time monitoring, and historical analysis, making it easier to identify and resolve issues. However, they do come with challenges like storage requirements, performance overhead, and data privacy concerns that need to be clarified and managed. So if you found this video helpful, please make sure to subscribe and hit the notification bell so you'll never miss a video, and see you in the future. Welcome back to our system design series. In today's episode, we are going to explore monitoring systems, a critical component in keeping distributed applications healthy, reliable, and performant. By the end of this video, you will understand what monitoring systems are, why they are essential, and how they help ensure your systems run smoothly and issues are detected before they affect users. Okay, so imagine you are managing a distributed application that serves thousands of users. To maintain high availability and reliability, you need to constantly track the health and performance of your system. Monitoring systems allow your allow you to gather data from all parts of your application, whether it's a server performance, database queries, or a network latency. So you can take action when something or somewhere goes wrong. So let's try to see an example. It's basically pretty simple. Let's say that we have our own server or our own system, our own microservices system, or our own distributed system, and we can monitor everything to gather all the informations and numbers we need to know if something is going wrong or not. So a monitoring system is a solution that collects, aggregates, and visualize data from different components of an application to track its health, performance, and availability. It continuously monitors metrics like CPU usage, memory consumption, traffic and network traffic, response times, and more, so that you can quickly identify and respond to issues. So, with a monitoring system in place, you can set up alerts that notify you when certain thresholds are exceeded. For example, if CPU usage exceeds 90%, or if the response time for an API calls increases significantly, you will receive an alert allowing you to investigate and address the issue before it impacts users. So let's talk about how the monitoring working, like how this process is working. So, oh no, 1 minute, monitoring. Okay, so monitoring systems work by collecting all the data and various data sources with your infrastructure. Like agents are typically installed on the server. So we have some sort of agents, and these agents, can I go back? Yeah. We have like some sort of, oh no, we'll have some sort of agents, and these like agents are typically installed on your servers, containers, and the other components to gather metrics. These data is then sent to a centralized monitoring platform where it's processed, analyzed, and visualized. So I guess tools like Prometheus or Grafana are pretty famous one. Grafana, I guess, is often used to visualize that data in an easy to understand dashboard. These dashboards provide a real-time view of your system performance, for example, helping you make informed decision about scaling, troubleshooting, and optimizing your infrastructure. So let's talk about what is the benefits of monitoring. We got maybe we have I have four things in mind. First thing is the proactive issue delegation. Monitor systems allow you to detect issues before they affect users by tracking key metrics and setting up alerts. You can take proactive measures to prevent downtime. The second thing is performance optimization, because monitoring helps you identify bottlenecks in your system, such as slow database queries or overloaded servers, allowing you to optimize performance and allocate resources effectively. Third, improved reliability. With continuous monitoring, you can ensure that all parts of your systems are functioning correctly. If a service becomes unavailable, monitoring systems can trigger alert, allowing your team to respond quickly. And yeah, this is the most important things that we can understand. Um, I guess yeah. To summarize and to sum it up, monitoring systems are crucial and critical for maintaining the health, reliability, and performance of your applications. They help your proactive detect issues, optimize performance, and response in incidents before they affect users. While they while they do come with challenges like data overloaded and alert fatigue, effective monitoring is a key component of any scalable and resilient system. If you found this video helpful, don't forget to like and subscribe and hit the notification bell so you'll never miss a video, and see you in the future.